Let's start out this lesson today with a quick warm-up. Just with a partner, I want you to try to write each expression as a single radical. Okay, pause the video and then come back. Welcome back. Let's start with part A. In part A, I'll just label it down here. We're multiplying the square root of 3 by the square root of 12. Because they're both square roots, we can do this. When I multiply, I get square root of 36, which just simplifies to 6. In part B, in this part, we're dealing with cube roots. They are both cube roots, so I can multiply straight across. 5 times 25 is going to give me 125, and that is a perfect cube. That is going to be a perfect cube of 5. Okay, in part C, which is right here, we've got fourth roots. The fourth root of 27 times the fourth root of 3 is going to give us the fourth root of 81, which if I look down here, 81 is a perfect fourth. It's going to be a perfect fourth of 3. 3 to the fourth power is 81. So I'll have just 3. Okay, in part D, they're both square roots, so I will divide those. I get square root of 49. Square root of 49 is going to reduce to 7. Here, they're both fourth roots. What does 4 over 1,024 reduce to? That's going to reduce to 1 over 256. I just put this in my calculator, press enter, and then I go to math, and under math I can choose fraction. So I call it math fracking, but that's how I got the reduced form so quickly down to 1 over 256. The fourth root of 1 is just 1. And what's the fourth root of 256? The fourth root of 256 is going to be 4, right? It's a perfect fourth of 4. So I get 1/4. Okay, and last but not least, part F, both of these are cube roots. So if I take 625 and divide by 5, I end up with 125 under that perfect cube. Okay, and then what is the cube root of 125? The cube root of 125 is just going to be 5. All right. So now that we've gotten our brains warmed up, just keep in mind you can use this reference sheet here to help you identify quickly those perfect squares, cubes, fourths. If you want to create your own sheet and not use this one, that's fine as well. But let's go ahead and move on to adding, subtracting, and simplifying radicals. So in this section, it says, I can use properties of radicals to simplify and write radical expressions in simplest form. Today, it's important that we understand what a like radical is. It says like radicals are radical expressions with the same index or root and the same radicand, which is just the number or expression underneath the root. Okay, so just looking at this, here's my index. You can see it's the type of root you have. The radicand is the number that's underneath the radical. Okay, and it doesn't necessarily have to be a number. It could be an expression. Okay, but we want to make sure that whatever the radicand is, whatever the expression is underneath the radical, that it's the same for it to be a like radical. Okay, and then we've got, of course, our radical symbol, which is this, and the entire thing we call a radical expression. Okay. So now we know what an index and a radicand are. Let's go ahead and start with example 1 where we're adding and subtracting like radicals. So in part A, are these like radicals? Do they have the same index? Well, let's look. In both cases, the index here is the fourth root. So yes, they have the same index. And then we need to also look at the radicand and make sure that the radicand is the same. Is the expression underneath the radical the same? Here is 10 and here is 10. So yes, those are the same as well. So we have the same index and the same radicand. So now that I know that they're like radicals, we can sum their coefficients. So here, when there's nothing written in, we're assuming that there's a 1 out front, and then there's a 7 out front over here. Okay. So 1 plus 7, that's going to give me 8 of those fourth roots of 10. Okay. I like to think about it like if I've got, 1 apple plus 7 more apples, then how many apples do I have? Well, I'd have 8 apples, or 8 fourth roots of 10. Right over here, keep in mind if I wanted to rewrite this, I could rewrite it as 2 times the 5th root of 8 to the 1st power plus 10 times the 5th root of 8 to the 1st power. Remember, this is power over root when we're looking at a rational exponent. Okay, in this case, are these like radicals? Yeah, they're both 5th roots, and the radicand is 8 in both cases. So we can combine those. I can either write my answer like this, where I have, let's see, that would be 12 of those 8 to the 1/5. Or if you want to write your answer in radical form, you can write 12 of those 5th roots of 8. Okay, either way. Do we have like radicals in part C? Is the index the same? Well, they're all 4th roots. What about the radicand? Is that the same? They're all 2x. So they are like radicals. All 3 terms are going to be like radicals. So how many 4th roots of 2x am I going to have? I've got -3 plus 8. So that's 5. And then if I add on 4 more, that would be 9 of those 4th roots of 2x. Okay. Down here in part D, do I have like radicals? Well, here I've got a square root, and a square root. Okay, so the index is the same. What about the radicand? I have 3, 2, 3. So they're really, there's one in particular that's not going to be a like radical. It looks to me like these are going to be like radicals because they're both square roots and both the radicands are 3. But this one is not a like radical with the other 2. Okay, so let's combine these. We have 6 and 4, so that's going to be 10 of those square roots of 3. And then I'm just going to keep the 4 times the square root of 2 separate. Okay. Notice that I cannot reduce the square root of 3 anymore, and I cannot reduce the square root of 2 anymore. Those are in simplified form. What about part E? Are these like radicals? I see all square roots. But here, what the radicand are all different, right? If I look under each radical, we've got 12, 3, and 48. So right now, none of them are like radicals because the radicands are not the same. But what I'm going to try to do is simplify first and see if I get like radicals after I simplify. Simplify before adding or subtracting to see if you get any like radicals. Okay, so let's go ahead and do that. Let's start with 5 times the square root of 12. What's the largest perfect square that 12 is divisible by? It would be 4, right? 4 is a perfect square. So if I reduce that, we'd have 5 times 2, radical 3. Or in other words, 10 radical 3. Okay, what about the next one? 2 radical 3. Is 3 divisible by any perfect squares? No. So I'm just going to leave it as 2 radical 3. So I have plus 2 radical 3. All right, what about the last one, the -3 root 48? Is 48 divisible by any perfect squares? Let's see, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. We have 5 squared, 6 squared, 7 squared. So 48 is not a perfect square. Is it divisible by 36? No. Is 48 divisible by 25? No. Is 48 divisible by 16? Yeah, it is. So 16 would be the largest perfect square. We could break that into 16 times what? It'd be 16 times 3 is 48, where 16 is the perfect part. Okay, and keep in mind we still have this -3 leading coefficient. So if I reduce the square root of 16 down to 4, that's going to leave me with a new leading coefficient of -12. And then we'll have the root 3. Okay, so see how I simplified each part? I simplified 5 radical 12 down to 10 square root 3. 2 radical 3 did not simplify, so I just kept it the same. And then -3 root 48 that reduced to negative 12 times the square root of 3. Okay, now that everything is simplified completely, now let's look to see if there's any like radicals. Remember, we're looking for the same index and radicand. They are all square roots. And if you look at what's under the radical, all three of them have a 3 as their radicand. Okay, so they are all like terms, so I can add the coefficients. So here if I have 10 root 3 and 2 root 3, that would give me 12 root 3. Okay, and then what is 12 root 3 minus 12 root 3? That's going to be nothing. So I end up with 0. What about in part F? Right now they are not like terms because one radicand is 54 and one is 2. But can I simplify this cube root of 54? Well, let's list our perfect cubes. We've got 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and I'm going to stop there just because 54 falls in between 27 and 64. So is 54 divisible by 27? It is. Again, we were looking at perfect cubes here because I saw that the index of all of these were cube roots. Okay, so that's why we're looking at breaking it into perfect cubes. So I've got the cube root of 27 times 2 would give me the cube root of 54, where 27 is a perfect cube. Let's reduce that. The cube root of 27 is going to be 3. And then the 2 is not perfect, so it stays under the root. Can I reduce the cube root of 2 any further? No, I can't. So that's just going to drop straight down, and we'll subtract off the cube root of 2. So we have 3 cube roots of 2 minus 1 cube root of 2. So that's going to leave me with 2 cube roots of 2. Right? If nothing's written in, we're assuming that there's a 1 here if nothing's written in. All right, let's go on to the next page here. In the next page, we're just practicing more multiplying. We're going to multiply first, and then we're going to combine like terms and add and subtract like radicals. So let's go ahead and take a look at this one. If we have a binomial squared, remember what that means is just to take that binomial and multiply it by itself. Remember, parts outside the radical are going to be multiplied by other parts outside the radical, and parts under the radical are going to be multiplied by other parts under the radical. So I'm going to have 2 root 5 times 2 square root 5. So the parts outside the radical are 2 times 2, which is 4. And the parts under the radical would be 5 times 5, which is 25. So notice we kept the 25 under the radical. Then I do my outers. Let's see. Again, we've got to make sure we're multiplying like parts. So here we've got 2 times negative y are both outside the radical. So I'd end up with negative 2y. And then you can see that we had a root 5 that was under the radical. Okay. Then I do both my inners. Again, the 2 and the negative y are outside the radical. And then the 5 is under the radical. Last times last, we have negative y times negative y, which would give us a positive y squared. Okay, let's reduce. The square root of 25 is just going to be 5. So I'll have 4 times 5. Here we have like terms because see how they're both square roots of 5? If I have negative 2y square root 5 minus another negative 2y square root 5, how many square roots of 5 will we have? We'll have negative 4y square roots of 5. And then we have plus y squared. Okay, so ultimately we'll get 20 minus 4y square root 5 plus y squared. It's fine to write it that way. If you want your higher power on the left, you can do that as well. So if you prefer to write it this way, that is fine as well. Okay. This one we're not going to be foiling, but we are going to be using the distributive property. Here, when I multiply these two guys together, the 5 is outside the radical, and then the 2 and 3 are under the radical. So 2 times 3 would be 6, plus. When I multiply the second round of terms, the radical 2 by the 3 radical 6, We have a 3 outside the radical, and then the 2 and the 6 are under the radical, so we would get root 12. Right now, I cannot combine these because they are not like radicals. The radicand is different. Let's try to simplify and see if then we can add terms together. 12, let's see, the largest perfect square would be divisible by would be 4. So if I reduce this, we'd have 5 radical 6 plus 3 times 2 radical 3. So I end up with 5 radical 6 plus 6 radical 3. And that's as far as I can go. Again, look, my radicands are not the same, so they are not like terms, so I cannot add them together. All right, at this point, why don't you pause the video and try some of these student practice examples. Hi there, welcome back. Let's see how you did. I'm going to start on part A and move through these pretty quick. So they're both fourth roots, so we can multiply straight across. We end up with, what is that, 81. So the fourth root of 81 would be 3. Also, you could have noticed this. 27, remember, is just 3 cubed. So when I multiply straight across, see how I have 3 cubed times 3 to the, if nothing's written in, it'd be first. So really see how I get 3 to the fourth? A fourth root just undoes a fourth power and leaves me with 3. It's another way to think about it. In the next example, if I divide those cube roots, we'd end up with the cube root of 125, which is 5. Cube root of 104, I don't think that's a perfect cube. Let's list our perfect cubes. We have 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed. I'm going to stop there just because 104 falls in between 64 and 125. What is the largest perfect cube that 104 is divisible by? Is 104 divisible by 64? No, it's not. Is it divisible by 27? 104 divided by 27. No, you get a decimal. What about 8? 8 does work. 8 times what is 104? 13, where 8 is perfect. 8's a perfect cube of 2, so we'll get 2 times the cube root of 13 as our answer there. Okay, down here, these are like terms. See how we have 9 to the 2/3 in both cases? So if I have 4 apples and 8 more apples, how many apples do I have? 8, 9, 10, 11, 12. We would have 12 of those 9 to the 2/3. All right, are these like terms? Yes, they are. They're both fifth roots of 12. So if I have 7 fifth roots of 12 and I take away 1 of those fifth roots of 12, I would have 6 fifth roots of 12 left. Right? If there's no coefficient in there, we're assuming it's 1. These right now are not like terms in part F because 5 and 40, those radicands don't match. Let's simplify to see if we can get like radicals. Cube root of 5, I'm just going to keep alone. 40 is not a perfect cube. What perfect cube would 40 be divisible by? Is 40 divisible by 27? No. What about 8? Yeah, 8 times what gives me 40? 5, where 8's perfect. Cube root of 8 is going to be 2. Okay, so if we have a cube root of 5 plus 2 more cube roots of 5, we would have 3 of those cube roots of 5. Right? When nothing's written in, we assume that coefficient is 1 that we combine with the 2. Okay, and that's it.